So for a circular cross section, it can be shown that the warping function psi is a constant, and in this case the expression for the torque, it reduces to the familiar equation where the J takes the form of the polar moment of inertia. Just look at the expression for J. So in this expression, the value of psi being constant, so these two terms would become 0, and as a result we'll get J equal to the area integral of x square plus y square over the entire cross section, and this is our familiar term, polar moment of inertia. The shear stresses take the form as shown here. So the shear stresses tau yz and tau zx are given in terms of the coordinates of the point. So for example, if you consider a point which is lying on x-axis, so at this location the y coordinate is 0, so as a result here the tau xz would be equal to 0, and only thing which would remain is tau yz, which would be given by the expression which is by this equation. And if you consider point on y-axis, we'll find that the x is 0, so as a result tau yz would be equal to 0, and tau xz would be given by the expression which is given here, and it would be the value of tau xz. So in this case we are considering this body to be subjected to the torque, which is a vector in positive z direction. So under the action of this torque, you can see that the nature of stresses is what we expect them to be using our familiar classical torsion theory. At any intermediate point, you will get the two components tau xy, tau xz and yz, and the resultant will be tangential. It can be proved that it is tangential to the geometry at that point, that is, it is tangential to the circle. Next we'll have a look at the elliptical cross section. For the elliptical cross section, again the psi can be shown to be equal to the expression what is given here. How to obtain these expressions, one would have to refer to the textbook. I am not covering it here. This warping function is interesting one as compared to the previous, where psi is constant, which means that all cross sections are going to remain flat. They are not going to have any warping, whereas in the elliptical cross section we are having warping taking place. If you look at the expression, it has got some constant in terms of the minor diameter and major radius of the ellipse and the product of x and y. It means that in the first quadrant and in the third quadrant, where the product xy is positive, if you note at this particular equation, it is b square minus a square, which is a negative term, so we'll get the uz as negative. So this particular quadrant, the surface will warp inside, and in the remaining two quadrants where the product is negative, the warping function will be positive, and these two surfaces will warp outside. That is, they will move along the positive z axis in these quadrants, and in the other two quadrants the cross sections will move in the negative z direction. So that is the nature of warping function for elliptical cross section. The expression for the torque and the expression for the shear stresses are as shown here, and it can be proved that the maximum shear stress occurs along the minor axis of the elliptical cross section. Okay, the discussion till now has been to find solution for bar of any cross section. So it is a general approach. However, for certain class of problems, that is for thin hollow sections, a much simpler approach can be used. Let's see how it is done. These sections are also known as the thin box sections. These sections are having a hollow cross section and the wall thickness there is small as compared to the other dimensions of this bar, and when they are subjected to torque, a much simpler approach can be used without requiring the complicated warping function and other details. In this approach, the concept of shear flow is important. Let's understand what is shear flow and how it is useful. So consider a small elemental segment of this particular body which is bounded by the edges AB and CD. Consider that corresponding to edge AB of this element, the shear stress is tau 1, and as you move ahead, the shear stress becomes tau 2. By the equality of cross shears, we know that on the face parallel to edge AB, the shear stress would be equal to T1, and the shear stress acting on along the edge CD would be equal to tau 2. So that is the starting point. Now for the equilibrium of this element which is bound by the edges AB and CD, the forces along z direction must be equal to 0. So we require the sigma fz equal to 0, which means that the force on edge AB because of the cross shear stress direction would be as shown here on edge AB face, and the force on CD face would be in the opposite direction by the nature of cross shears. So force acting on edge AB would be given as tau 1 multiplied by area of the face corresponding to edge AB, which would be given as length AB multiplied by thickness at that point. So we are considering at this edge the thickness is T1, at the other edge the thickness is T2. So that is the force which is in negative direction, and the other force in positive direction is tau 2, that is shear stress multiplied by CD and multiplied by the thickness T2 would be equal to 0. If you consider the length AB and CD as unity, so they will be unity, and then this equation becomes tau 1 multiplied by T1 equal to tau 2 multiplied by T2, and this would be true for any cross section along this box section. So this quantity tau 1 into T1 is termed as the shear flow, denoted by notation Q. So the shear flow is defined as the product of shear stress at the cross section of a thin box section multiplied by the thickness at that particular location. Now you would ask why the term flow is used. So it can be explained thus. It has got a physical analogy with respect to flow. If you consider this box channel or the box cross section as a channel through which some fluid is flowing, so we are considering that a fluid is flowing through the wall of this cross section, and the flow rate of the fluid is given as small q. You will find that as the cross section changes, so wherever the cross section is small, you will find that the velocity is high, and wherever the cross section is bigger, the velocity will be smaller. So the velocity will keep on changing from one point to the other point depending on the width of this channel, which is nothing but the thickness of this cross section. Now you can see the analogy between the flow rate and the shear flow, and the velocity and the shear stress. So in this case, the shear flow indicates the analogous fluid flow through this channel, and the stress at any point in this cross section is the velocity of the analogous fluid passing through this cross section. Now let's proceed to find out how to find the stresses in these thin box sections. For this purpose, consider a small segment PQ of within this box section, which is having a width of ds, and the local thickness at this particular segment is given by small t, and O is the centroidal axis about which the torque T is getting applied, and the distance of this segment from the origin O is given by the value h. Now if you consider the forces acting on this cross section, so we have the cross section which is having a length equal to ds and thickness equal to t. If you consider that a shear stress tau is acting on this particular cross section, so shear stress acting on this segment is given by tau. The total force which is acting on this segment would be given as dF equal to tau multiplied by t into ds. Now this particular force which acts on this cross section is going to cause a moment about the origin O. So the contribution of this force towards the moment, which is given by dm, would be given as df multiplied by the distance h. So this would be given as tau multiplied by t multiplied by ds multiplied by h. Now from the previous discussion we know that this tau into t is nothing but the shear flow Q, and ds into h can be written in terms of the area which is formed by the triangle whose base is ds and height is h. So ds into h can be written in terms of the area of this triangle which is subtended by this segment. So if the area of this triangle is dA, so this particular area dA would be given as half into base into height of that triangle. So the ds into h can be written as twice into dA. If we add up all these moments, so this is the moment which is caused by force acting on a segment of length ds. Similarly, there are many segments. For each segment, if we calculate the value of this moment and add them together, you will get the total moment acting on this cross section, which is nothing but the torque acting on this cross section, would be given by the integration of this dm. When you integrate it, this dA term will become total area, so we'll get the total torque as 2 multiplied by Q multiplied by total area, which is subtended by all the segments of this particular box section. So we get the equation for the torque in terms of the shear flow, which includes the term for stress, shear stress, and the area A. So note that this area A is not the area of cross section, but it is an area enclosed by entire midline of the cross section. So here we are considering that this ds is measured at the middle of this cross section. So ds is considered at the mid surface, and hence the total area is also computed in terms of the midline of this particular box section. So by using this equation, if you know the value of torque, you can find out the shear flow, and hence you can find out the shear stress at any point of this box section. The expression for the angle of twist per unit length can be obtained, the derivation of which I am not covering here. The expression for angle per unit length is given in terms of the shear flow Q, the area A, which is area enclosed by the midline of the box section, the shear modulus, and the path integral or the line integral ds by t. So if this cross section is having a variable thickness, so at one point the thickness would be t1, at another point it would be t2, and so on. So along this path S, we are summing up the ratio ds by t, and how to implement it in actual case I will illustrate with the help of an example.